Still working on section 2.7, the related rates section, and we're looking at example 2 or 8 here, where we have two cars are riding on two different roads that meet at 90-degree angles. Car A is 3 miles south of the intersection, traveling north at 40 miles an hour, and car B is 2 miles east of the intersection, traveling at 50 miles an hour. How fast is the distance between the two cars changing at this moment? Okay, so, you know what, let me use a different color. Let's set up our right triangle. We know we have these two cars traveling and the roads are perpendicular. And so obviously we can form ourselves a right triangle. Two cars are riding on two different roads. They meet at right angles. Car A is 3 miles south, so this will be my car A, 3 miles south, traveling at 40 miles per hour. So it's headed north at a rate of, so let's go with, we could go N and S, I guess. So dN dt is 40 miles an hour. And car B is 2 miles east of the intersection, traveling at 50 miles an hour. So ds dt is equal to a 50 miles per hour. And since he's going left, actually both of these would be shortening, wouldn't they? They would both be negative because the distance between them, I think we'll put them both at negative. And they are, car B is 2 miles at the intersection. The question is, what's the distance between them doing? And this distance would be shortening as they drive towards each other, right? Oopsie. And just want to get those extra lines off there. All right, so that distance would be shortening. What should we call that distance? I don't think I want to go D. Let's call it, let's just call it Z as the distance between them. Now, how do I write an equation about this? Well, I could have S squared plus N squared equals Z squared, because it is a right triangle. All three things are changing as this triangle changes, right? All three things would be changing. So we need variables in those spots. Let's do our derivative. 2s ds dt plus 2n dn dt equals 2z dz dt. And noticing that they all share 2's, let's divide every single term by 2. So the 2's are gone, just to make this a little bit simpler. Now, I had changing values, or rate values for ds. ds was a 50 miles an hour. And n was 40 miles an hour equals, well, z, I don't know. That's what I'm trying to find out, is dz dt. And then it said at this moment, so at the moment where we had some different rates or some different mileages, where car A is 2 miles away from the intersection, that would be like n equaling 2, wouldn't it? And the other one was car B. This was miles, not minutes. Whoa. Okay, 2 miles away. The other one was 3 miles away. And so that would be, my S value would be 3. So on our triangle, we lock in a triangle with a 2, 3 there. And we got to find out Z. Well, Z would be the square root of leg squared plus leg squared. So 9 plus 2, or 9 plus 4, or 13. So the square root of 13. That would be the distance of Z at this freeze frame moment. All right, so S is 2 I'd have a 2 times 50 plus an n at 3. I think I goofed up. I have s first. Okay, s is 3. N is 2 times 40 equals a z, which is root 13, times a rate at which it's traveling. So we'd have 150 plus an 80 equals the square root 13 dz dt. That makes a 230 on the left side. We would divide by the square root of 13, and that would be our dz dt. Okay, so if we get the calculator out, we can take 230 divided by the square root of 13 and get 63.791 miles per hour is what the dz dt, or the hypotenuse, the distance between the cars, is changing at a rate of. Now here's the problem. I really think that should be a negative because that distance is shrinking. Oh, but it's miles per hour, so that makes sense. Okay, so positive. That's the miles per hour, that the rate at which the cars are changing. Okay. Let's see. Let's go into the next problem since we're just at 5 minutes here. And I gotta see if I can find it, guys. There's another problem. The shadow problem. So a man of height 1.8 meters walks away from a 5-meter lamp. So my guy is 1.8 meters tall. The lamp is 5 meters tall. And he's walking away. A man walks away from those at a speed of 1.2 meters per second. Find the rate at which his shadow is increasing in length, and how fast then is the tip of the shadow moving. So those are two different questions. We're going to do part A first, and then we'll talk about part B. Okay, so the trick on this type is that we have similar triangles. We know that this angle is the same. These are both right angles, and then because these run parallel, vertical lines there, this angle and this angle would be congruent. So by angle-angle similarity, we have triangles similar. So that allows us to create some distances here. We want to find the rate at which the shadow is increasing in length. So let's let the shadow be y and this be x. So I've got a segment here that I'm going to call x, and then I've got the segment here. If you want to use color coding, maybe that would be a good idea. I'm going to let the green segment be y. So let's try and set up a proportion. We know we have similar triangles, and that allows us to do proportion work. Now we just got to remember our triangle, our geometry work, right? I could say 1.8 meters is similar to y, or is 1.8 is to y like 5, the vertical distance, is to, tricky part, we got to get the full distance because we're on the big triangle. So the big distance is an x plus y. X plus y. Hopefully that makes sense to you. I did vertical height is to horizontal height, like vertical height 5 is to horizontal distance x plus y. Now let's work a little bit of the proportion magic. Let's do the cross product on this. That way I don't have to start delving into quotient rule. So I get 5y equals 1.8 x plus y, parentheses around that to keep working. 5y equals a 1.8x plus a 1.8y. and subtract. Let's bring like terms together. You know, you always want to simplify before taking derivatives. So the easier my equation looks, the better luck I'm going to have with getting the correct derivative. I think we've got this whittled down as far as we can go. So now it's derivative time. So derivative time. Derivative 3.2 dy dx equals 1.8. What's with the dx? They're so wrong. Dy dt. Dx dt. Okay, I need to look back because I bet I was given some more information that I did not write down. So I'm going to reread. A man of height 1.8 meters walks away from a 5-meter lamppost at a speed of 1.2 meters per second. And that's the man walking away at a speed. Okay, so it's the man that's walking away. His speed of walking is dx dt from the lamppost, and it's a 1.2. He is increasing his distance, so dx dt should be positive. I would expect his shadow might be lengthening or it might be shortening. That's kind of tricky. Let's wait and see here. So dx dt, I can fill in the fact that he was walking away at a speed of 1.2 meters. 1.2 meters per second. And solve for dy dt. So I had a 3.2 there. We're going to divide to get dy dt equals a 1.8 times a 1.2 divided by a 3.2. Calculator time.